Okay, thank you very much. So it's for me a great pleasure to be lecturing at this kind of mythical winter school. Generations of statistical physicists have participated to it. Actually, I never came as a student, and I was always very envious of all my colleagues who were participating and were telling these great stories. So I'm happy also to be the first. I wish you a great school, and also get the chance really to study and learn things which are not exactly in your field, but like keep this kind of knowledge with you for the future. So as Filippo said, I'm going to be talking about, let's say, quantum chaos, but really focusing on kind of statistical properties to it, so what we call the eigenstate thermalization and recent advancements. So to give you first some words, let's say, of motivations, what one has in mind are kind of the venerable questions of statistical mechanics, which is how can we understand irreversibility when the laws which describe the individual constituents are actually deterministic, no? So emergence of irreversibility. Now, reversibility. Okay. So as you learned in your lectures of classical statistical mechanics, the way, let's say, to understand these issues is, or a limit in which we're interested is when we have many degrees of freedom, no? And so what we learned is that in this kind of limit, the only way we can approach the problem is using statistical approaches. Okay, so this kind of idea is the same that also applies in the quantum regime, where recently there has been, let's say, a renewed attention due to the incredible experiments that they can do on the field of quantum simulations. So, so you may know that now, over different platforms, experimentalists are really able to, let's say, identify and manipulate individual many-body quantum system and to study their dynamics at unprecedented time scales in condensed matter physics. And let's say that this has motivated and stimulated also questions which were somehow unthinkable in the kind of standard paradigm. And those are also kind of questions that we may be interested in. And I would say that another big source of motivation is the which goes in hands with the field of quantum simulation, are clearly quantum technologies, where now we have these great machines, okay, that now maybe seem quite small, but ultimately a quantum computation is nothing but an evolution, a many-body evolution. No? So we can really think, let's say, about quantum computers as many-body systems, computers. Okay. Okay, where h bar is equal to 1. Okay, now all this kind of motivation. So you will see this kind of last questions has really motivated, let's say, the study of new kind of discrete many-body systems, such as quantum circuits, and you will hear a lot about this kind of discrete models in the lectures by John Chalker. Now, the goal that we kind of set ourselves is to learn as much as possible from kind of coarse-grained description, so really in this kind of statistical sense, as you know very well. And so what we are going to use is a lot of statistical notions, and in particular random matrix theory, which allows, let's say, to find some universal properties of this kind of generic scenario in which we want to understand the dynamics of chaotic quantum systems. Okay, so what I'm going to be talking, let's say, is far from being exhaustive. It's kind of really personal account of things that I like and I find interesting. So this is really not let's say, by no means general. So let me just give you a small plan of what we are going to discuss. So today I am going to give a general introduction about equilibration and thermalization. Then I'm going to provide some hints of random matrix theory, so which is a field that is very important on its own, but you will see enters, let's say, in a very loud way also in what we are going to discuss. Then I'm going to really focus on many-body Hamiltonians and discuss this Eigenstate Thermalization Hypothesis, toy models, and let's say open problems. And then I'm going to give, let's say, so the Eigenstate Thermalization Hypothesis has been, since now I would say 20 years, the way we now understand this framework. So how can we, the emergence of irreversibility, but recently it became clear that that was not the full story. And what we have started to understand, and this is somehow the beyond, is that really we needed some different math to gain intuitions. So I'm going to tell you about free probability. Also here, it's going to be quite an introduction because it's a big field. And then I'm going to tell you how this enters in this kind of full ETH. So the description of many-body systems. So, and then discuss free probability and ETH. Okay, so this is the plan. I started to type some lecture notes that you will find both on the website, so they're not still there today, but they will be uploaded soon, or on my website, chaos.org/teaching. Okay, there are also some exercises, and yeah, I will tell you which one you're supposed to do. Okay, so if you don't see, you're supposed to tell me. Okay, good, you see. You're also supposed to interrupt me if I go too slow or too fast. And in particular, if you find typos and errors, which is highly probable, you're invited to let me know. Okay, so let's start from the first task, which is the study of equilibration and thermalization. Okay. So to set the stage, what kind of models we're looking at? We're looking at systems with n degrees of freedom. Okay. So when we study many-body quantum systems with n degrees of freedom, we have a problem which is defined on a Hilbert space whose dimensionality is exponential with the number of constituents. This you know very well. And then I'm going to be focused on closed quantum systems, so such that the evolution that we're studying, there is a unitary operator which determines the evolution. Okay. And now, in particular, what I'm going to be focusing on is Hamiltonian evolution. So I will also mention somehow dynamics dictated by Floquet circuits, but in my description, I want to focus on Hamiltonian evolution, where the dynamics, so the unitary operator, has the following expression. And now I want to restrict to the case in which my Hamiltonian is local. What does it mean? That the interaction among the constituents happens mostly locally in space, so there is a notion of locality. Okay? The Hamiltonian is local, and then it has no symmetries. So I really want to take what we usually refer a generic many-body system, okay? Now, this kind of generic, there is a sort of abuse in the field to say what is generic, but okay. So what I want to say is local and non-symmetries. Okay, and then we can discuss a bit better. And now let me just write down an example that you can have in mind, so just to let's say, focus or to think about something of a typical Hamiltonian that one wants to study. You can imagine a one-dimensional array of spins 1/2, so in which you have, for instance, some term along Z, and then you add some field in one direction, and then you need to add, okay, so let's put here some parameter, GW Here some interaction, some field in some other direction. Then you may want to also, let's say, break translational symmetry, really to be in the most generic case, okay? So this is a kind of non-integrable Hamiltonian, the kind of that is widely studied. So usually in the field there is always numeric on this kind of model. So this is one-dimensional. So here the number of constituents corresponds to the length of the system. So I will often, when I write L, I mean N, and when I write N, I mean L. Okay. So this is yeah, this is, and these are Pauli matrices, okay? So these are spin 1/2, and this is the kind of model that we have in mind. Okay, let me leave it here. Okay, so given this, yes? Yes, you can have you can have many symmetries. No? So in this case, you can have let's say global symmetry. For instance, if I don't put this, you can have Z2 symmetry. You can have translational symmetry. There are many kind of symmetries that then make the problem more structured and then sometimes even integrable. So I want to consider a situation which I have no clue of how to solve the problem, and actually these very often, so also the title quantum chaos, in kind of the many-body scenario, quantum chaos is referred as a nickname for kind of many-body systems which we cannot solve. And so for this reason, we kind of need statistical approaches, and it's what we will do today. I'm just adding, let's say, a term on one side just to break every kind, also translational symmetry. So you can add whatever you want here. It's not summed. Yes, yeah, just a different coupling on one side, okay? This is just really to break also translational symmetry and whatever. It's not needed, but. What? No, here I want to break everything. Yes, it's an open chain. This is just it's just to have something in mind, you know? So this is a system with locality. So it's, let's say, defined Hamiltonian by a set of Pauli spins over sites. You can think about something like this. Then exactly, you can play every game you want, no? 1L. I want to consider a situation in which I don't know the solution of the model, okay? But I want to say something about it. Okay, so now let's consider, let's say, a quantum quench protocol. Okay, so I initialize at time t0 equals 0 my state in some initial state psi 0, which is a pure initial state, and you can think about it as the ground state of some Hamiltonian H0. Okay, and then at time t, I evolve it with a different Hamiltonian H. So then I have that psi of t is equal to minus IHT over H bar psi 0. Okay. So the Hamiltonian H is different from H0. So now, unless H0 and H commute, okay, this state will undergo some non-trivial evolution. Okay. Now, this kind of initial state, you can of course rewrite it in the basis of the Hamiltonian. So let me now here write the spectral decomposition of my Hamiltonian, which will enter a lot. Okay, I also want to call the dimensionality of the Hilbert space D. So D is going to be the dimension of my Hilbert space, which is huge, and then I have a spectrum. Okay, so once I write down the spectral decomposition, I can of course write my initial state as EIT, CI0, EI, where Ci 0 are my overlaps. Overlaps. Okay. I'm just rewriting the initial state. And now this kind of scenario in which you change abruptly, let's say, your Hamiltonian from some h0 to some final h, it's called quantum quench. So you always find it with his name. And sometimes one refers to a global quench, where let's say, so why a quantum quench? The idea is that you see h0 as an Hamiltonian, which depends on some initial parameter h0, small h0, you don't see, yeah? You will see. Here, I just want to kind of set the notation, okay? This first hour is not going to be thrilling, but, okay. I kind of want to set the stage such that then all these notions are kind of simple for you. Okay. And then I kind of am quenching over some final parameter, okay? So here, or let's say, let me call this parameter G. Okay, so here you can imagine that you start your initial state, which is all polarized down, which would be, let's say, the ground state of this with G equal to infinity, and then you quench it to a finite value of G. So this is the kind of quantum quench, and then people talk about global quenches, if this G concerns, let's say, all your degrees of freedom, or local quench, if G couples only to 1 degree of freedom, like in this case. Okay, but okay, this is just a name, it's not very important. Now, what is the main feature of this kind of quantum quenches is that you're introducing energy in the system. Why? Because your initial state has a given energy. Okay, so this is the initial energy. And this is usually extensive. Okay, so also during these lectures, I'm going to indicate with capital letters, let's say, extensive quantities, and with the little e, or the little letters, intensive quantities, no? So usually initial states have extensive energy, and then typically, or we want to consider states which have sub-extensive energy fluctuations. So which means that the energy variance of the initial state, which is let's say, also extensive. Okay. So why the energy fluctuations are sub-extensive? Well, this really, you know it from StatMech, which means that, let's say, the fluctuations of the energy over the energy square is small. So this is 1 over n. Okay, so this is the kind of quench scenario in which we have an initial state, which have this kind of small fluctuations to respect to the energy we have in mind. Okay. I forgot to say, since we are in this kind of regime, a one-dimensional system with spin 1/2, this is really the full many-body regime, where basically there is no small parameter. So you are going to see that I will always set h bar to 1. So here I lost it already at the second line, the h bar. And I'm going to mention really explicitly when we need h bar, okay? Okay, but now why I'm saying so that we are putting energy? So my initial state now has this energy which is high, let's say, has a why? Because okay, the energy density is finite, and you can also think about it as an increase of temperature of your initial state. So of a temperature, so this is equivalent. Now, you may be wondering which temperature, so you are not, your system is closed, you're not coupled to any environment, but what we really mean here is somehow a sort of microcanonical temperature, beta E, which we can define thinking about some thermal energy density, some canonical energy density, at this inverse temperature, beta E, okay? So when you hear people when you hear people talking about infinite temperature initial states, what does it mean? It means that the associated energy of the initial state is the one that you would have with a thermal density matrix which has infinite temperature, okay? So again, this is just setting, let's say, the scenario. Okay, and now let's go to the heart of the matter, which is how can we understand this kind of quantum quench in a meaningful way. Now, the way we kind of learned how to do this is by looking at the dynamics of local observables. Observables. Okay. So this is really the essence of how we understand now this kind of out of equilibrium scenario. So in particular, we want to monitor how a local observable that I'm going to indicate with the letter A evolves in time. Okay, so this is the kind of object that we're going to be focusing on. And now, why am I interested in something like this? Well, this is really in the full analogy with what you would do in the classical limit, in the classical case. So, in the kind of out of equilibrium scenario that you could have classically, the typical sketch that one does is the study of an initial state, okay, of a many-body system, which could be, let's say, a drop of ink in a glass of water. So this is a system with many degrees of freedom, and then you put some blue ink in your glass of water, and then you wait, okay? Maybe you can steer, and that would be, let's say, an external drive, but if you wait long enough, this will start, let's say, diffusing, and then if you wait even more, you will have a uniform, let's say, okay? So this is with time. Okay. And now we kind of want to do the same thing. So in this case, you would study as an observable, let's say, the density of the white particle, okay, the blue, whatever, the local density on some region of the blue particles. So this would start, let's say, from 0, then grow, and then saturate to a value of 1/2. Okay. And now, in this kind of many-body scenario that we want to think about, we have exactly the same kind of protocol, no? We want to study a local observable. But now, which kind of local observable, to respect to the example that we were making before? Well, it's clear that A could be, for instance, a Pauli matrix over one site in some direction. Or let's say, maybe some observable which has support on two sides. Okay, this kind of local objects. So you will see, and we will discuss here and there, why this concept of locality is important for what we want to talk about. So this is, no, sorry, we already had that. This sketch. So what I want to consider here is an observable which has some local support A, okay? Like this kind of two. Okay. Very good. So let's now write down this. Yes. Yeah, no, this is a good question. There are some works which now I would refer as a little bit old, in which they were studying exactly this question, how big should be the support of A, and kind of defining, so this is a paper by Tarun and Grover kind of pointed out that the length, the support of the length should scale at can be extensive, but should be smaller than half the system. Yes, I mean, this is the limit that you should have in mind, but I want to treat everything for finite L, in particular for for the ETH, is a statement in the limit of large system size. And you will see that there is always an implicit, let's say, separation of scales. So you want, yeah, we're going to talk about that. Okay. Okay, so we want to rewrite this object here. So I put the kind of rewriting that I had above with my overlaps. I'm actually going to drop the 0 there. So this is Ci, Cj star, and then I have Ei, A, Ej, e to the I, Ei minus Cj, T. Okay. Now, what you see from this object, so what do we expect? We expect that the dynamic of this object will have the phenomenology that we're talking, that we kind of sketched here. So what we expect, if the system thermalizes in the sense that we know classically, that at very long time it will attain a stationary value, so some stationary value, let's say A of equilibrium. Okay, and now I'm going to define this a bit better. And basically now the kind of goal of all this discussion is to provide the formalism to understand this equilibration scenario and even more dynamics at equilibrium, how this is encoded in the eigenvalues and the eigenvectors of the Hamiltonian. So you see, this kind of local observable, we rewrote it in terms of here, the eigenvalues, and the eigenvectors through these matrix elements, Aij, okay, which contains information about the eigenvectors, clearly. So all our goal is, is to find the appropriate description for our eigenvalues and eigenvectors such that what we know classically makes sense. So a very fair question from you is where quantum mechanics enters in this kind of thermalization description. And one could also answer, at the mesoscopic level, it never enters. It's just that we want, let's say, to find the appropriate quantum description, which is based on the eigenvalues and eigenvectors, at least for what I'm going to say for the first part. Okay, good. Now, to kind of, let's go here. Okay, to kind of formally study, so let me now define, so a system equilibrates so we say that a state and Hamiltonian, so there is equilibration if local observables converge to an equilibrium value at infinite times. So if the limit of t going to infinity of a of t is equal to an equilibrium value. Okay, and now this mathematically is studied via infinite time average. So that I'm going to denote in the following way, which is the limit of t going to infinity of 1 over t, the integral of a of t in the t. Okay. So this is a mathematical tool. And now let's put inside this inside this. Okay. So we have, okay, let's start from here. We have that the infinite time average is equal to a constant part. So here I first set I equal to j. If I is equal to j, I have no time dependency here. So this average cancels. So I get sum over I, ci square AII plus sum over I, plus the limit of t going to infinity, the integral, and the t, and then I have the sum over I different from j, okay? So I'm separating the summation in indices which are the same and indices which are different. Okay. And now the point, which is now important, is that in this, let's say, assumption of genericity, what I can assume is that there are no degeneracies. So no okay, which is kind of something that makes sense if I'm considering this kind of system without conservations and without symmetries. So what does it mean that I have no degeneracies? That EI is equal to EJ only if I is equal to J. Okay. So since we are doing this no degeneracy assumption, this integral will vanish. Because if I is different from J, I'm integrating at very long times a function which is oscillating. Okay, so this has to vanish. Okay, this. Yeah, there is 1 over t, thank you. Not here, here. Thank you. Okay, this vanishes. Then mathematically, you may invoke the Riemann-Lebesgue theorem, but physically, the kind of idea is that here you're really summing over many different frequencies which are different. Okay, so there is destructive interference and this oscillating part vanishes. Okay, so if this vanishes, what we have done, we have rewritten the equilibrium, so the infinite time limit. So this object here, we can rewrite it. This is a constant, okay? This is our equilibrium value. How did I call it in the notes? Okay. So this is the so-called average over the diagonal ensemble. You can see there. Okay, so what did I do? I basically rewrote, okay, maybe this, kind of. So I introduced an effective density matrix, so a description of the density matrix, which I'm called diagonal, this stands for diagonal ensemble. So this is the sum over I, Ci, EI, EI. Okay. This diagonal ensemble, this has all the classical information of my initial state. Why? Because it's it's diagonal in the energy eigenbasis, and it encodes all the amplitudes of my initial state, which I erased, but okay. So you remember Ci, EI, psi 0. Okay, so why I'm saying all the classical information? Because it's only the modulo square. So there is no information about the phase. This infinite time average, okay, so yeah, this is, let's say, it's a good question. So you're asking, if this is what you're interested in, why are you studying the infinite time average, okay? So this is a mathematical trick that I want to use to make precise statements. But of course, let's say physically, but this is also, by the way, what you do in statistical mechanics, now when you define ergodicity. But this, you also know that in order to see, let's say, the equilibration of of your drop of ink, you don't have to take really the infinite time average. Namely, this will happen on a finite time scale. At this level, this infinite time average is a mathematical trick or a mathematical description of what is going on at large times. Yeah, but for this you need, let's say, ETH, not 12. Yeah, but to make it go to 0 precisely, I mean, at long times. No, but okay, you have to take then the limits n going to infinity and time going to infinity properly, no? Because you could have recurrences at long times. I'm just doing a definition. Exactly. No, this is what I want. I want just to give a definition of an object which makes sense when I send t to infinity. Okay. It tells you something about the infinite time average of this limit. Yes, it could oscillate forever, yes. Yeah, it can. I'm just taking the infinite time limit. Yes, what you want is that the fluctuations are small. We don't know yet. This is kind of left as an exercise. Okay. Now, but to properly define, so in my definition of equilibration, for now, I just want to talk about this kind of. So the definition is the one above, but I do want to talk about it through this infinite time average. And now a system thermalizes if this equilibrium distribution corresponds to the one given by statistical mechanics. Namely, if the limit which is the diagonal ensemble, okay, let me repeat, if the average over the diagonal ensemble corresponds to the microcanonical value of the operator at the energy density given by the initial state. Okay. And now this definition is for finite t. Okay. And now this, in other words, is let's say there are two elements. So first of all, it's requiring that this diagonal ensemble corresponds to the microcanonical distribution. And let's say this is something that by studying the kind of states, the kind of initial states that we introduced before, it's appropriate expectation. Why? Because so if I plot here my CI modulus square, we said that as a function of the energy eigenvalues, we said that this kind of initial state as average energy E. So it's centered around an average energy E, and then it has small fluctuations. So this is the variance over D, scaling like 1 over square root of n. So I can imagine that this kind of, so for the kind of initial states that we defined, the kind of diagonal ensemble has this microcanonical structure. But now, if a system thermalizes or not will ultimately depend on the structure of Aij. Okay. Why? Because, okay, here I'm asking something about the distribution of the initial state, but let's say here, do I have a stick? Yes. Here, in the definition of, let's say, this asymptotic value, I have two things. So I have this overlap, and I have the diagonal part of my observable in the energy eigenbasis, and this clearly, okay, I have to say something about this, and you will see that this is somehow the content of ETH. Okay. Yeah. No. So this is, I wrote it in this way. So because I want to, also in a finite system, I will also always have recurrences. So if I wait long enough, this kind of object, even if, let's say, the properties of these behave in the appropriate way that you will discover, you will always have recurrences. And you kind of, sending n to infinity, you wash away these recurrences. So this limit is important. Okay. No, this is Aij, sorry, thank you. Yes, the eigenvalues are independent of. Yeah, because the evolution I'm studying is just a unitary evolution with a fixed Hamiltonian. So, okay. Okay, so yes. Well, why only local observable? Let's say there are several answers to this. An answer is that I want to, let's say, describe what I could physically access. So this is kind of the original motivation, which is you want to access, yeah, you can measure only things which are local, given a geometry. But now, you will see now in a few minutes that this also has a kind of an important meaning, because also to understand this kind of thermalization, usually you need to think about a bath. And now, only if you have, okay, so I have my one-dimensional chain, and I'm studying something which is local. Okay, the rest of the system will act as a bath for my subsector. Yes. Yeah, because this effectively acts as a microcanonical distribution. Okay, in the large n limit, this is behaving as if you had only an eigenstate. But we're going or you're going in the exercise to discuss this a little bit better, why, let's say in the large n limit, the two things are the same. Okay. But also, yeah. Yes? No, because the probability of having, we're going to discuss this in a little bit, but the probability of having eigenstates whose level spacing is zero is zero. Okay, so let me just, okay, before the break in 10 minutes, let me just do a little comment on our definition of thermalization. You see, we are asking very little, no? We are asking that a given class of observables, local observable, in the large n limit, go to their equilibrium distribution. And this is really, let's say, a definition of thermalization of ergodicity, which is very similar which is also present in the classical, okay, let me write it here. which is also present in classical statistical mechanics, which is the approach of quenching. So I don't know how many of you have heard about this approach to statistical mechanics in 1949. So quenching was a mathematician, and there is a very beautiful little booklet which is called the Mathematical Foundation of Statistical Mechanics, in which actually, let's say, not really going against Boltzmann, but saying that in order to prove thermalization, one actually needs or wants to ask, let's say, less than the ergodic hypothesis that you may remember. And so quenching in the classical setting really asks only these things. So he says we should think about system in the large n limit. We should require thermalization only on a subclass of observables, that makes sense. And you may have, let's say, failure of thermalization in isolated points in phase space, what he had in mind. And here in our setting is that you can always find some initial states which fail to thermalize. Okay, but what you want to describe is kind of scenarios, generic scenarios, okay? So such as the one that we are describing here. So I wanted to make this comment about, the fact that this kind of definition is really similar to the one that we have also classically. Okay, so let me conclude this with these 5 minutes by pushing a bit more this kind of local perspective, which is related to the question that your colleagues just asked. Opla. Okay. Okay, so here we are really talking about observables which are defined only on a local support. No, I'm calling it A of A. And now this kind of point of view by looking at local observable is similar to the one that we would do classically. Classically, we define phase space by a set of conjugate variables, and then we study only a smooth function of those conjugate variables. Now, in this example, the Hamiltonian I erased before, I also want to have this kind of picture in which I have only observable, which are smooth functions, let's say, of let's say the operators which define my Hamiltonian, no? So I want smooth function of those which are defined locally. So now the important thing is that when studying these local observables, so every time I have a local observable which is defined on a local support A, all its information is encoded in the so-called reduced density matrix. So this is equal to this, where rho A is the trace of A bar psi psi. Okay. Okay. So this object encodes all the local information. And now local thermalization, so the fact that going for T going to infinity, this corresponds to the microcanonical ensemble, implies that locally my asymptotic initial state looks thermal. So to be more precise, we have that the limit of T going to infinity, okay, let's preserve, of rho A of T, this is equal so this is the local thermalization. Okay. Why? Because I'm looking at observables which are defined on a local support. So what I'm saying is that the asymptotic reduced density matrix looks thermal. Okay. Now, this, let's say, in this kind of description, we fix very few things. We fixed only the initial energy of the initial state. So we're saying that all initial states which are compatible, which have the same energy density, attain, let's say, the sort of same asymptotic distribution along times. So we have a sort of loss of information, no? Because I'm saying that every initial state will go to the same value. And this is kind of a paradox because my evolution is unitary. No? So in principle, globally, information should be conserved. So you may wonder, where did all the information go? And the answer, let's say, so The paradox, yes. So, loss of information plus unitary. And now this apparent paradox is kind of restored by the fact that all the information goes non-locally in the system. So remember, we have this kind of scenario. All the local information spreads non-locally in the system and goes into entanglement. So what we can always look at is, let's say, the von Neumann entropy of the reduced density matrix. So this is the entanglement entropy. So I'm not going to talk a lot about this quantity, which actually has a huge role also in the study of all this field, and I'm sure that many of you know what it is. Okay, but if you don't, it's not very important. Okay, but the idea is that this quantity, okay, quantifies how many, say, bell pairs are shared between A and the rest. Sorry, A bar is the rest of the system, okay? So in this picture, this is A bar. Okay. So this quantifies how much information is shared non-locally between A and A bar, and saying that the system thermalizes, so that the system locally looks like a thermal density matrix, means that this kind of quantity, so the entanglement entropy at long times, should look like the thermal entropy. Okay, so let me put the limits in the proper way. Okay. Now, what is one of the main properties of the thermodynamic entropy? That it's extensive, no? It's extensive. So actually, so let me divide the entanglement entropy by NA, where NA is the number of sites which are on my interval A. Okay. So what if this object, let's say, is thermal, it means that the entanglement entropy is the same as the, let's say, thermodynamic entropy density. Okay. In other words, okay, so this is a bit more formal, but in other words, as long as little a is much smaller than the system size, what I'm saying is that the entanglement entropy, so this is for large times, okay, has the same prefactor as the thermodynamic entropy, and scales with the volume of the interval. So this is something which is referred to as the volume law. Okay. This, I mean, I don't want to enter too much into this discussion, but I think it's a crucial part of this sort of study of local thermalization, is that while thermalization happens, also information spreads non-locally in entanglement. And this implies, by this analogy between thermal initial, this kind of idea of local thermalization, that the asymptotic reduced density matrix obeys volume law. Asymptotic state obeys volume law. Yes? To be precise, yes, yes. So you need it to be big, not necessarily extensive. There is, so I'm going to use it in the same way. Thank you for the question. So what? So the kind of this sort of this final note was to say that all the thermalization we have in mind, I'm going to discuss about, is always local thermalization. Okay. In principle, you can ask the same question even on observables which are large. But I want to keep instead in mind the fact that observables are defined on a finite support which is much smaller than the whole system. Yes. Yes, are equivalent. Or let's say for these lectures, they're equivalent. I just want to consider this kind of local thermalization. So what it means is that I want to have a well-defined classical limit in mind, which I am able to do only if the observable is local to respect to the whole system size. But I do think that especially in this kind of new quantum technology era of quantum simulation, this kind of non-global, non-local observable are now accessible, and it is a very interesting question to understand how much I can push, let's say, the support of the operator. So generally, and this goes back to the question that someone asked, and A over L is taken to be, let's say, much smaller than 1/2. So your support has to be, can be extensive, but should be much smaller than L over 2. And there are other kind of entanglement entropy argument that we can make, but maybe we should have a break. Is this working? Yeah. Okay.